All right, so you've got your notes there. I'm going to start real quick with those, but I want to highlight first, the last 2 pages of that are a sample form. If you're 3 pages from the end, you'll see a page there that talks about positive evidence for a young earth or a young recent creation. I will just tell you in advance, we're not going to get to that part. I printed these notes a couple weeks ago and had a plan to have maybe more than 1 week in this section. That won't happen. We have just today for this section. So I want to give you a couple of things really quick so I don't forget at the end if we're pressed for time, in their book recommendations. And then next week, I plan to also give a list of recommended books that if you have interest in any of these topics, you can get a hold of and get more information. So the first book is the Creation Answers book. This is put out by Creation Ministries International, Dr. Carter's group, Dr. Carter, who was here with us several weeks ago. And this book just has chapters on everything we've talked about. And much more. And so if you just want to be able to have, and it whittles it down to the essentials. There are some sections of technical jargon in each section, but it's because they're really dealing with the issues and the information. But if you're a novice like me, you can wade through it, and it will help you get the gist of what the answer from a scientific perspective and a biblical perspective is to whatever question you have about creationism. So that's a great book. Couple others on the topic of geology, since we're really gonna hit 2 main topics in it, but other things that may interest you. I picked up this one when Dr. Carter was here, The Frozen Paradox, about ice cores and deep time. Fascinating. I haven't read the whole thing yet, but what I have read is great, very helpful. That's one of the key issues. We'll talk about the issue of time in geology today. It's a significant issue, just like in cosmology. But this is a great book and a very rarely talked about, even though it's a significant issue from a creationist perspective. So that's a good one. There's another book, Biblical Geology 101, also from Creation Ministries International, and then a book called The Young Earth by John Morris, I believe grandson of Henry Morris. Might be son, I can't remember the relationship. But great books. They'll be in the list that I provide for you at the end of the series. But this Answers book, I should mention, is in the Resource Center today if you wanted to get a copy of it. I highly recommend anybody who likes these topics pick a copy of that up. All right, so we explored at the end of last class very briefly our 4 potential solutions to the problem of distant starlight from a biblical cosmology perspective. And we tried to make sense of how does our observation of this distant starlight fit in with a normal reading of the Genesis account. And so we talked about, for example, the white hole cosmology model. And that one even includes a proposal of what scientifically might have been happening. Obviously, God's creating the universe. It's a supernatural event. There are things going on that won't fit into just natural physics as we observe them today, but that's the same for all models. The Big Bang says the same thing as we talked about. Physics breaks down when you get back to the beginning. But as far as how might God have done things so that, for example, in a young universe, we could see those distant stars, had some great explanation of that. None of those theories that we talked about enjoy widespread acceptance in cosmology today. Like the Big Bang does, but we even talked about how support for the Big Bang is waning. It's still the majority opinion, but it has its own problems. But those 4 positions we talked about from a creationist perspective offer some great answers. We said, which one of these is correct? And I said, we're not sure. Maybe none of them is correct. Maybe we have yet to discover why we can see distant starlight in a young universe. The science is always changing. And as we gain a better understanding of new evidence and of the old evidence, better understanding of the old evidence, we will come up with new theories to understand. That's how science works. So we ended last week with a reminder that what we can be sure of is that we are still learning and we have a lot to learn. And we can be sure that the biblical account of Genesis has not been shown to be incorrect. So when we start with that account and we then have a wealth of explanatory options available to us as we explore the amazing creation that God has put us in. So We are going to shift our attention then from the stars to the ground beneath our feet. So you can turn to page 1 on your notes, and we'll attempt to engage the same activity of beginning with God's Word and looking at the evidence with that as our hypothesis. And we'll just do it in the area of geology. So let me talk a little bit about geology's rocky start. Just as I did in cosmology, just as I did in the subject of science as a whole, I want to start off with a little bit of history. Geology encompasses a wide range of disciplines, including the study of rocks, minerals, landforms, the structure of our planet. And so geologists investigate how the Earth has changed over time, the forces that shape it, and the resources it provides. And like other issues of our areas of science, geology is comprised of many diverse disciplines. So geology is not like a single thing. You can see there the list of various disciplines that span a spectrum of specialties. So we've got, for example, physical geology focuses on the physical features of the earth, things like mountains, valleys, rivers, the processes that create them. You've got the area of historical geology, studying the earth's history, things like the evolution of life is a key area people who study geology are subjected to. The changing environment over time. There's mineralogy, the study of minerals, what they're made of, what are their properties. There's the study of, it's called petrology, the study of rocks, their formations. So you've got different rocks. Some are formed by sediment being spread by water and then settling. Some of them are spread by heat, melting substances, and they flow as lava or magma, and then they solidify. So you've got petrology, you've got stratigraphy, the study of the layered rocks and their relationships to one another. Related to that, sedimentology I mentioned earlier, that's the study of rocks laid down not by heat, but laid down by water. And then paleontology, which studies fossils, past life forms that we find evidence of in the rocks. And then you've got other things like geochemistry and geophysics. And as we've done in the previous section, like I said, I want to start with a little bit of history. How did we get to all these diverse disciplines in the study of geography? So the study of the earth, what it's made of, materials, goes back to probably 3rd or 4th centuries BC, and then but that's just surface level, like people looking at and going, that's a weird formation. I wonder what caused that. But very little development in the subject over the next 1,000 years or so. In fact, the term geology wasn't really used, not just that term, the English term, yes, but in general, it wasn't thought of as a field of science until about 1603. And then about 100 years after that, you've got a guy named James Hutton, who's recognized as really the first modern geologist. He was a Scottish farmer. He was a naturalist, so he took a view that says, not just methodological naturalism that says if you want to learn, you can't, just try to study and cause and effect, but philosophical naturalism. He took the view that everything kind of just is. There's no superintending force guiding it. And so if you look up his biography in curriculum that's recommended by the American Museum of Natural History, you'll read this about him, and you see the quote there at the bottom of page 1. In the late 18th century, when Hutton was carefully examining rocks, it was generally believed that the Earth had come into creation only around 6,000 years earlier, and that the fossils were remains of animals that had perished during the biblical flood. So he's got this view of naturalism. He's living in a world where that is really, nobody else thinks that. Nobody else thinks that it's just all natural. Most people view creation as God's direct act, and even people who may have various views of that, really the idea of the global flood is pretty widely accepted. But being a naturalist, Hutton was interested in explanations of the formations in the earth around him that he saw that were supportive of his naturalistic philosophy. And he wanted something that didn't require the widely held model of, and you see the term there, biblical catastrophism. You'll hear that referred to. That's the idea of Yes, the world operates based on laws of science that we can observe and deduce and learn about. But as a part of that, not everything has just gone on and on without change from the beginning. You remember Jesus talking about this, that people say things have gone on from the beginning, nothing has changed, and they ignore the evidence of Noah's flood. He proposed two key concepts upon which a new model, in contrast to biblical catastrophism, a naturalist model based on two things. First was subterranean heat, so volcanoes and things like that. And then the second is what he called the theory of uniformitarianism. And I've got that in quotes there because that is his phrase that he gave it, he dubbed. The theory of uniformitarianism is the belief, and this is a quote, a belief that geological forces at work in the present day, barely noticeable to the human eye, yet immense in their impact, are the same as those that operated in the past. And so I think, let's see, that was at the top of page 2 if you're following along in the notes. So at this time, geology wasn't widely embraced, as I said, not just naturalist view of geology, but geology in general was not embraced as like a normal science on par with biology or cosmology. It was viewed as more of like storytelling about the earth. That you looked at evidence and you're just kind of trying to figure out and connecting the dots, telling a story about what you found. Not like a hard science that you could go into the laboratory and test something to come up with an objective answer. And so that same Museum of Natural History curriculum that I referred to earlier says this: Hutton's ideas about uniformitarianism and the Earth's age were not well received by the scientific community of his time. His ideas were falling into obscurity when Charles Lyell, that's who you see on the screen there, Charles Lyell, a British lawyer and geologist, wrote a book called The Principles of Geology in the early 1830s. So Lyell's book promoted Hutton's principle of uniformitarianism. So 50 years laying dormant, falling into obscurity. Lyell finds it and says there's something to this. So his studies of rocks and the processes that form them, and the idea that the Earth was possibly over 300 million years old. So Lyell, in his 3-volume Principles of Geology, had a lasting influence on the geologic community and public at large, who eventually accepted uniformitarianism and the millionfold age of the Earth. The principle of uniformitarianism became so widely accepted that geologists regarded catastrophic change as heresy. This made it harder for ideas like the sudden demise of dinosaurs by asteroid impact to gain traction. So here is this curriculum recommended by the Museum of Natural History saying what I'm saying here, and that is that eventually this naturalist approach of uniformitarianism caught on, and in fact it caught on so significantly that it was the doctrine that, you look at the processes, erosion's happening right now, and so you see rock sediment being laid down that way. That has to be how it happens. So you look at a thing like the Grand Canyon, and you go, all right, erosion and water laying down sediment, man, that would take a long time to build the Grand Canyon. So that's the theory then. You have to have long ages because of that. In fact, that is why this quote from the curriculum says, that's why it took an idea like an asteroid crashing into the Earth and killing the dinosaurs, took so long for that to catch on, which is like the predominant view of what happened to the dinosaurs in the scientific community today. It didn't catch on because you can't say catastrophe interrupted present processes. That's heresy. And that's not my word. That's used by the Museum of Natural Science, heresy. So before we continue considering the impact of the eventual acceptance of Hutton's ideas, I just want to highlight the pattern that we observe already several times in this series. Often when something new comes along in science, it faces opposition. So another geologic example of this can be found more recently in the last century. See the quote that I've got there? At the bottom of page 2, it was a century ago this spring, this is written back in 2012, so a century ago, a century and a decade ago now, that a German meteorologist named Alfred Wegener proposed that the continents had once been massed together in a single supercontinent and then gradually drifted apart. He was, of course, right. Continental drift, and more recently the science of plate tectonics, are now the bedrock of modern geology, helping to provide vital answers to questions, or vital questions like where to find precious oil and mineral deposits and how to keep San Francisco upright. But in Wegener's day, geological thinking stood firmly on a solid earth where continents and oceans were permanent features. The quote goes on, "We like to imagine that knowledge advances fact upon dispassionate fact to reveal precise and irrefutable truths. But there is hardly a better example of just how messy and emotional science can be than Wegener's discovery of the vast turbulent forces moving within the Earth's crust. As often happens when confronted with difficult new ideas, the establishment joined ranks, tore holes in his theories, mocked his evidence, and maligned his character. It might have been the end of a lesser man, but as with the vicious battles over topics ranging from Darwinian evolution to climate change, the conflict ultimately worked in the benefit of scientific truth." So whether you agree that the conflict worked to the benefit of scientific truth when it comes to the debate over evolution or climate change, it is clear that trying to get to truth in science can be messy and is rarely dispassionate. And this is an example from the 1900s. It says, that quote says, by 1930s, his theory had been rejected by most geologists, and this is what I want to highlight, sank into obscurity only to be resurrected as a part of the theory of plate tectonics during the 60s. So rejected for 30 years, and what's happening during those 30 years? The citation says this is what's happening. As often happens, when confronted with difficult new ideas, the establishment joined ranks, tore holes in his theories, mocked his evidence, and maligned his character. Now, that's the kind of thing that you see happening to creationists, right? So you have somebody like Ken Ham make this statement. Yeah, the scientific community is just putting up a wall. They're not listening. They're not following the evidence. Ken Ham from Answers in Genesis says it, and he will be dismissed or mocked simply because he's the one who said it. But that acknowledgement is from the Smithsonian Magazine. That's not some creationist, hack magazine. So for a current example of this as well, I'm going to skip over it. You can read this, but there's a current scientist, Sabine Hassenfelder, who left the Scientific Academy because she got sick, basically, of the roadblocks getting in the way of her actual research because it didn't bring in grant funding. And there's another video that I reference later on here that she made that is her going over correspondence she received from a colleague who says, shut this down, quit saying this stuff in public, we have families to feed, basically. So I'm not doing this to say scientists are dishonest or that they're diabolical. My point in calling out the way scientists who step out of line often get attacked and marginalized is that I want to highlight that these are just people doing research, studying, and they bring to it with their worldviews, and they have, you look at the paragraph there, let me see where I'm at in my notes that you've got here. Bottom of page 3, I say there, the point is to underscore the fact that having a worldview and permitting that perspective to be your framework in interpreting observations and evidence, which is a charge often used to discredit creationists, isn't unique to us. It's true of all scientists because all scientists are humans with worldviews. Science, ironically, isn't something that just happens in a laboratory vacuum. Theories are proposed and considered, rejected, or embraced by human beings who bring their philosophical assumptions and other more mundane motivations. And you see the footnote there to the video I was talking about. Very practical motivations to their scientific endeavor. So as noted in the series, because of this, science often precedes one funeral at a time. It just means that you got to wait for the old guard who's not willing to listen to new ideas to pass off of the scene. While it's true that creationists have their commitment to their worldview that motivates them to look for explanations of the evidence that fit their pre-existing network of beliefs, so do naturalists, so do all scientists. All right, back to, we were considering the impact of the eventual acceptance of Hutton's ideas. Note that, once again, we've observed several times, sorry, this jumped back at me, reading the same notes there. All right, back to the impact of the eventual acceptance of Hutton's ideas. He proposed that subterranean heat and uniformitarianism could explain the state of the Earth if there were long eons of time to allow for gradual changes. So we noted that his ideas were initially not received, but that Charles Lyell's 3-volume work, Principles of Geology, brought them to the fore, helped them gain acceptance. And this impact of sea change in geology on other fields of science, such as biology, just can't be overestimated. So look at the quote that I've got there about a contemporary of Lyell. I say there that a contemporary of Lyell, Charles Darwin, took the book, The Principles of Geology, on his 5-year trip. Darwin used uniformitarianism and deep geologic time to develop his initial ideas about evolution. Lyell was one of the first to publish a reference to Darwin's idea of evolution. So the Museum of Natural History curriculum cited earlier agrees the impact of this theory can't be underestimated. And then I've got a quote there that talks about this, and I'll read this quote as well. This means that the rates at which processes such as erosion and sedimentation occur today are similar to past rates, making it possible to estimate the times that it took to deposit sandstone, for example. It became evident from such analysis that enormous lengths of time were required to account for the thickness of rock layers that you find exposed in places like the Grand Canyon. So uniformitarianism is one of the fundamental principles of earth science, says this citation from the Museum of Natural History's curriculum. It's one of the fundamental principles of earth science. Hutton's theories amounted to a frontal attack on popular contemporary school of thought known as catastrophism, the belief that natural catastrophes, such as the Great Flood, could account for the form and nature of a 6,000-year-old Earth. The Great Age of the Earth was the first revolutionary concept to emerge from the new science of geology. So this shift happens in geology in concert with early developments in cosmology that we've already considered, and it plays a role in shaping the thinking of naturalists in the 19th century. All right, let's move on to the dawn of the 20th century on page 5. At the dawn of the 20th century, science is said to have taken another giant leap forward due to the development of methods for obtaining precise, and I put it in quotes here because this is a term, it's a technical term they use, absolute dates for geologic formation. So before this, you've got geologists digging up rocks, looking at the thickness of layers, looking at the fossils found in them, and kind of going, all right, so it probably, based on the rate of sedimentation we see happening right now, it'd take X number of years for this to happen. And they did come up with very large numbers. But when they developed this process called isotopic dating, and I'll explain a little more about that, it allowed them to look at materials in the rock, perform a calculation, and then what they thought is happening then is kind of looking at a clock. You know, they thought we're looking at how much of one chemical and how much of another that it yields is there. It's like a clock. We know the rate at which this happens. So these absolute dates could then be applied to fossil sequences containing datable material, effectively converting the previous, what they called relative ages, to absolute ages. And this development is claimed to and popularly understood to remove all subjectivity to dating methods used in geology. And so that's why they use the term absolute date. But creationists have made some very good arguments to the contrary. You know, there are still things in geology that are difficult to explain from a creationist perspective, and so that has to be acknowledged. But geologist John Woodmarat has produced a very technical and devastating critique of radiometric dating. And that book that I mentioned, the Creation Answers book, chapter 4 of that book details his findings and then some other relevant research in this area. And I want to spend some time going over that. We're going to spend the majority of the time today, we'll spend all the time we have left looking at this because it is foundational. If there is a problem with the dating methods, essentially the model, the naturalist model, kind of crumbles. And so in that respect, this is the first and strongest positive proof for a recent creation. So let's take a look at it. Modern dating methods. At the dawn, sorry, that's not the right notes here. Let me see if I can shift there we go. Oh, that is the right notes. There we go. There are a variety of radiometric dating methods used today to give ages of millions or billions of years for rocks. And what they do is they take relative concentrations of what they call a parent element and a daughter element. So I'm going to rattle off some details. If you're a sciencey person, this will make sense to you. If you're not, I'll show you a graphic in a second that might help, maybe. So potassium-40 decays to something called argon-40. When I say decay, you've got an element that's unstable, it's radioactive. Over time, it decays, it breaks down and turns into a different element until it settles in what's called a stable isotope, one that's not, it is stable. It's not unstable, it's not radioactive, it doesn't decay. So you've got, in fact, I'm not even going to read them. You've got them there in your notes at the bottom of page 5. And what I want to say about those is, so you've got the name of a element and a number, like argon-40. So what that's doing is if you've got like the periodic table, each element on the periodic table, the reason it's a distinct element is it has a distinct atomic number. That's how many protons are in the nucleus of that atom. And then the number, like argon-40, talks about how many total molecules there are in that element. And as an unstable element decays, the protons and neutrons, some of them convert. And so you have neutrons changing over to protons, and so it's changing the atomic number, which changes it to a different element, and then the number indicates how many total molecules are left in the nucleus. So if that didn't make sense to you, don't worry, you don't have to understand that. The key is you have to understand that elements in the rocks, some of them break down and change into other elements. And we can watch now and we know what rate that happens at. So theoretically, you could say, oh, if there's this much of one and that much of another, you could say this much time passed. But there are some, as I say here in your notes at the top of page 5, there are some unprovable assumptions that go into that, and here they are, 3 of them at least. First, that the starting conditions are known, for example, that there was no daughter isotope available or present in the rock when it solidified. So you're assuming if the thing goes from argon-40 to, what did we say, potassium, or potassium-40 decays into argon-40, you're assuming there was no argon-40 there when the rock solidified. There wasn't already argon-40 there. You can't know that. Second, decay rates have always been constant. So could something have happened? Uniformitarianism says yes, decay rates have been constant. But could there have been something in the past that happened to cause decay rates to change? We're going to see that that's very likely. Number 3, systems were closed, so nothing leaked in, nothing leaked out. Those are the 3 assumptions. Geologists use a number of techniques to try and ensure that these assumptions that they use are correct, but they're still unprovable assumptions. So let's talk about the problems with other problems with the dating methods. This first one that we just went through was that there are unprovable assumptions. Those unprovable assumptions lead to a bunch of other problems. First of all, bad dates. As you can guess, a process that requires the kind of assumptions that I listed, those 3 assumptions, might yield bad dates because you're making assumptions you can't prove. Well, I call them bad dates because how do you know they're bad dates? We're dating rocks that nobody was there to see form, right? Well, researchers get results that give them a date different than they expected. So like they find a fossil in a rock, for example, and they have this preconceived idea that that fossil's from an animal that lived X number of years ago. Well, now they have an expectation of how old the rock is. When they send it to the lab to get dated, if a date comes back that's not in agreement with when they think that fossil lived, it's a bad date. I'll talk more about this. Let's talk specifically about how this happens. When researchers get results anytime that's discordant with what they expected, they come up with explanations for causes of why their date would be out of range. And again, I'm not trying to ascribe nefarious intent. This would make sense if you had a high level of confidence in your model, just like with cosmology. If your model's right, well, we must be reading the data wrong, and so you calibrate. The need for this kind of posterior reasoning or after-the-fact reasoning should be a clue that there are problems with radiometric dating. The Creation Answers book provides an example of how this reasoning played out in the dating of Australopithecus ramidus fossils. So it cites a 1994 Nature magazine article and says most samples of basalt closest to the fossil-bearing strata gave dates of about 23 million years ago. So they find a fossil, they test the material next to it, comes back 23 million years, and they decided, well, that's too old because this fossil doesn't fit that age scheme. So they looked at some basalt further removed, farther away. They took 26 samples. 17 of them gave a date within their acceptable range of about 4.4 million years. That's what they were expecting. So the other 9 samples gave much older dates, and so they decided those must be contaminated. Stuff leaked in or leaked out. They discarded them. That's how radiometric dating works. It's very much driven, and this is still me quoting there, it's not my words, it's very much driven by the existing long-age worldview that pervades academia today. So the chapter provides another example. I'm not going to go over the details there for you. It's there to read, but suffice to say they switch until they get the date that they expected that matches. And again, that doesn't indicate that they're dishonest, but it highlights that they have a paradigm that's constraining their understanding of and interpretation of the evidence. And so with that in mind, the Creation magazine article talks about this second example. A scientist can't do experiments on the events that happened in the past. They don't measure the age of rocks. They measure isotope concentrations. They measure a ratio of how much of this and how much of that. But the age is calculated using their assumptions about how those things got there that they can't prove. All right? So one more example of this. Let's see. No, next section, related to this. Sorry, my notes aren't shifting the way I thought they would. The subjectivity of dating methods isn't just me, Mr. Creationist, making an inference because I'm an apologist and I have to explain creationism. It's readily acknowledged by the experts who run the labs who do these tests on the rocks. How is that? Well, here's a picture of the website of one of these labs that does radiometric dating that we're talking about. And this is the page, the form on their website where you fill out the details to submit a sample of material of rock to them for dating. And they include a question in this section that asks for details about the sample to be tested, and they ask the person submitting it to tell what is their expected date range. So there's the question on that chart there. It says estimated age range. It's asking, what do you expect? So that question's there. In the back of your notes, the last 2 pages of your notes, I downloaded their paper form. Same question is on there. Imagine with me if you had your doctor prescribe a lipid panel for you. He thinks your cholesterol is high. You got to go get your blood tests. And so you go to the hospital, you go to the blood lab there. They give you a form to fill out before you get your blood drawn. And on the survey or on the questionnaire that you fill out to turn into them, it says, how high do you think your cholesterol is? Well, you ask the person at the desk, why do you need to know how high I think my cholesterol is? Well, we want to rule out the bad numbers from the good numbers. I think you would probably be looking for another blood lab. And I don't say this to cast aspersions. I highlight this to show that This is not objective. If it were an objective test, you could send to different labs with different methods and no input from the submitter, and you should be able to know what the result is. It should be objective. Within margin of error, I have to say that. That's fair. Every lab test has margin of error. Second, the more rigorous version of radiometric dating that uses what's called isochrons, and we don't have time to explain what this is, but it adds a fourth metric. Normally they measure 3 things. You can see 4 dots on the graph here. This has so frequent instances of what they call bad dates that they have a whole crop of terminology that's grown up to describe them. So they have things called apparent isochron, mantle isochron, pseudo-isochron, secondary isochron, inherited isochron, erupted isochron, mixing line, and mixing isochron. And I'm just trying to drive home the point that if methods used for dating rocks were objective and reliable, it should not be necessary to calibrate our results with a priori or before experience assumptions of the inquirer, and then select them from among categories of explanations of why you got some undesirable results. All right, so next section, let's see, we're on page 8. Testing samples of known age. Another indicator that the reliability of these standard dating methods should be questioned is their tendency to produce incorrect ages on samples of known age. The following example